How do Laplace transforms derive transfer functions? Imagine trying to understand how a system responds to different signals. Instead of working with complicated differential equations, we use a special mathematical tool called the Laplace transform. This tool helps us change the equations from the time domain to the frequency domain. When we do this, the equations become much easier to work with because they turn into algebraic equations. In control systems and signal processing, a transfer function shows how the output relates to the input of a system. It is written as a ratio of the Laplace transform of the output to the Laplace transform of the input. To find this transfer function, engineers start with the differential equations that describe the system. For example, suppose we have a system described by a second-order differential equation that involves the output, input, and some constants. The first step is to apply the Laplace transform to each term in the differential equation. The Laplace transform of a derivative involves the variable s, which stands for complex frequency. For the first derivative, it becomes s times the Laplace transform of the function minus the initial value. For the second derivative, it involves s squared times the Laplace transform minus initial conditions. If the system starts from rest, the initial conditions are 0, simplifying the calculations. Once we transform all the derivatives, the differential equation turns into an algebraic equation with the Laplace transforms of the output and input. We then factor out the Laplace transform of the output. The resulting expression is the transfer function, which is a ratio of the output to the input in the S-domain. This transfer function provides a way to analyze how the system behaves for different types of inputs. For example, if the input is a step signal, its Laplace transform is 1 over s multiplying the transfer function. By this gives the Laplace transform of the output, which we can then invert back to the time domain to see how the system responds over time. In practical control system design, transfer functions are used to analyze stability, design controllers, and predict how a system will perform with various inputs. They also help in creating block diagrams that representing different parts of a larger system, making it easier to understand and analyze complex control systems. In summary, Laplace transforms turn differential equations into algebraic equations, making it straightforward to derive transfer functions. These functions then describe the relationship between input and output in a way that simplifies analysis and design in electrical engineering.